Now it is section 4.7, Newton's method, which is sometimes called the Newton-Raphson method. The Newton method is a computational technique to find solutions of fx equal 0. A value of x where f is 0 is called a root of the function f, and a solution of the equation fx equals 0. However, in this section we call such x sometimes root, and sometimes a solution, or simply sometimes 0. Okay, here is the Newton method. We have to find x such that fx equals 0. However, and for general function f, it is not easy to get x directly, so that we may start with an approximation. So let's say x0 is an initial approximation. So look at this figure. In this figure, what we have to find is this point. But assume we start with this initial approximation, x0. Then for this x0, here we can find the point here, and then we can find the tangent line. Once it is differentiable, f prime at x0 will be the slope, so that we can formulate the tangent line. Then now we try to find x-intercept, and that x-intercept x1 is considered as an updated approximation. And by using this one, x1, now we can make again tangent line and try to find the corresponding x-intercept. Then we call it x2, and which is again more updated approximation. We repeated this computation to get better approximations. That is geometric interpretation of Newton method. Now, we can formulate the Newton method mathematically in this way. Let x0 be an initial approximation. Then we can find f of x0, and once f is differentiable, then we can find f prime at x0. And by using slope point form, we can formulate the tangent line. And here, we have to find here x-intercept. In order to do that, we set y equal 0. Okay, so that equal 0. Then we solve it for x. Then we can recheck that one. Algebraically, you can do it quite easily. When f prime x0 is a non-zero, then this is well defined, so that that value will become now x1. Okay, so that is the updated next approximation. We repeat this step to find new approximations, better approximations. So here we formulate Newton's method. Start with the first approximation, and you may try to use graph of y equal fx to get good approximation. Now here, use the first approximation to get a second, and use the second to get a third, and so on. And so that eventually, by using an approximation old value, xn, and for xn, you can find the function value and derivative value, and as far as the derivative value is non-zero, then this fraction is well defined, and this algebraic computation will make here a new value, which is geometrically the x-intercept of the tangent line formed at xn and f of xn. So that is from x0 you repeatedly compute updated values. Okay, that is the Newton method. Okay, here we need to approximate the positive root of the equation x squared minus 2 equals 0. That equation came from this one. Okay, here let's say and x equal square root of 2. So we want to find square root of 2. And from this one, if we square both sides, then x squared equal 2, and we move this to left hand side so that x squared minus 2 equals 0. So once we find the positive root of the equation, then that will be square root of 2. Okay, so the problem is the same as find square root of 2 by using Newton's method. Okay, but here for that equation, for this f of x, f prime is now 2x, so that, and we try to put here for f of x, and that is xn squared minus 2, and f prime xn must be 2xn. So exactly we follow the formula here. So we reach at that one. Now you can separate out, so that half is now go out, and this will make xn. Now that one will make minus 2 over xn. Now one more time, you can simplify. So xn minus half xn makes half of xn. Now here that negation, and now that negation makes positive, so that here we have that is 2 of xn. So that's a final the formula for xn plus 1. Okay. So that can be implemented in this way in MathLab. Okay, let's start with 1. Right now, x0, that means that we said x0 equal 1. Now, the right side, that is half, that's a half, and xn is all the value. On the right side of equation in computational algorithm, now that is all the value. So xn, now plus 2 over xn, and divided by 2. Then that will be here xn plus 1, new value. So here for start with x0 equal 1, we are doing 6 iterations and try to print out the quantities, now x values along with n here. So the x1 to x6 are given here. Okay, now this value is quite accurate value of square root of 2. And let's see detail with a little bit change of the program. Okay, for that one, we try to compute this portion. That portion is basically from old one, old value. Now that is a sort of a correction term. So we try to here save this portion to h, and x minus h will make a new x. Okay, so that is now h is x minus 2 over x. Okay, that is x minus 2 over x divided by 2. That is exactly the correction term, and the term is subtracted to get new value. The reason we are doing this way is that we want to see how the correction term is changing. And here now, for each iteration, we are now printing out. The output is given in this way. Okay, the xn are the same as earlier here, but now look at here the h value. That is correction values. Correction values are rapidly decreasing to become 0. Here, 1 digit, and now that is basically 2 digit, and in fact, this is 2 digit accuracy. This is about now 30 digit accuracy, and there's about 6 digit accuracy, and that is 12 digit accuracy, and so on. Is rapidly reducing and converging to 0. The correction value is not really error. However, we'll see in a next example that this correction value is more or less around the error, and now so that this one is for that xn, for example x of 5. Once correction is given in this way, then this quantity is involving around the error about that amount. So that's the reason by checking the correction value, we can see the accuracy of the iterates. Okay, now let's see this example. Find the x coordinate of the point where the graph y is x cubed minus x crosses the horizontal line in y equal 1. Okay, so the first equation is graph in this way. That can be written as now x and x squared minus 1, so that x plus 1 and x minus 1. So that there is minus 1 here, 0 here, and 1 here. So that the graph of function is given in this way, passing this point and passing here, and passing here, and passing here. That is now graph of that one. Okay. Now y equal 1 is here, that one. So that is y equal 1. We have to find that point here. That's the question now. So we have to solve that equation by moving 1 the other side now, so that we have to solve the equation fx. We define this as fx, then we have to find root of f. Okay. Here, once x equal 1, then for f of x, the value is minus 1. Once the point is 2, then the value is 5. So by using intermediate value theorem, we know that the solution is between 1 and 2. So here in the solution, we start with 1.5. We know a solution between 1 and 2. Okay. Now here, for f of x, we know that is the derivative is 3x squared minus 1, so that the Newton's method can be formulated in this way. xn plus 1 is same as xn minus, that is f of, top portion is f of xn, the bottom portion is now f prime at xn. Okay, so that algorithm can be implemented in this way. Here, now fx, that is for in each iteration, now start with x0 is 1.5, and at each iteration we try to make here f of x, that is saving basically f of xn. Now this term is now correction term, f of x divided by this part is the same as here f prime at xn. So here there's correction term, and for all the value, the correction term is subtracted and to get here new value. Now we are printing out xn, and now the correction value here now f of xn, and at xn the function value f of x is now computed here now. But in fact, the f of x is old one, so that when you try to look at the output, you have to look at for the last column, the row below. Okay, here we have. Okay, here we have. Now that's x1 to x6, and here the correction values, and that is f of xn. Now, in fact, for that updated one, for example, x4, the correction is this one, and then at the moment, in fact, f value is that one, because we are using, okay, in the printout, all the values used, so that for that x4, in fact, so we make some simple printout, but anyway, for that x4, already is updated value, and at the moment the correction value. Now fx is measured along with earlier value, so that here the corresponding f value is that one. So it is really 0. Anyway, even though one grid is shifted here now, that is 30 digit and 6 digit, 12 digit, the same over there, f value is now 30 digit, 6 digit, 12 digit, accuracy is like that. So that by checking the correction term, once correction term is small enough, then you can say that the corresponding xn is good enough. Okay. Okay, here now for the Newton method, and we can say this here: the Newton method does not always converge, particularly when the initial approximation is not accurate enough. And for example, now in this figure, that's what we have to find. But once you start with here, then tangent line, and then here x-intercept. From this one, again, go to the curve and make a tangent line. Then that will be now out of the domain, so that in this case, mostly the Newton method will break down, so that it's not convergent. If Newton method does converge, then it converges to a root. When Newton method converges to a root, it may not be the root you have in mind. So it can converge to something else. We'll see here examples. Okay. This is what we want. But if you start with far away, then now from this point, you can make a tangent line and x-intercept, that is updated iterate, and now go to curve and make one more time tangent line, so that here updated value will be here, so that eventually it'll converge to that root. It's not what you want to get. But however, once it is convergent, then it is a root. The reason is basically the initial approximation is far away from the root you want. even though sometimes you start with near around root, but depending on the function shape, you can get something else. In this figure, x0 is near around root you want to find. But now, because of this function shape, now tangent line hit here, x-axis here, and again from this updated point, you are making tangent line. Then now here you can find x-intercept and go to the curve and tangent line and hit the x-axis so that the iteration may converge to something else, not what you want to get. So it can happen. So here we have a theorem, convergence of the Newton's method. Here, assume the function has a second derivative, continuous second derivative, and at x hat, f is 0, which means that x hat is a root, a solution of fx equals 0. And now at the root and derivative is non-zero. Earlier when we tried to formulate Newton method, we assumed that, okay, in algebraic manipulation, we assumed that here f prime at x0 is non-zero. Of course, later on, all the way here, f prime at every iterate should not be 0. So that always non-zero, then it's okay. So that, and we may assume here that at the root, the f prime is non-zero also. And another condition is here x0 is chosen near to x0. We cannot say how near, however, and always there is a neighborhood around x hat such that once you choose x0 inside the neighborhood of x hat, then the Newton's method generates a convergent sequence satisfying this inequality. That's error for xn plus 1, the difference between the iterate, new iterate, and the root. And now that is a difference between the old iterate and the root. So here, so we call it error. Error in the next level is bounded by here error, the previous level squared. So that once it is, for example, 10 to the minus 2, then it will become 10 to the minus 4. In the next iteration, that will become 10 to the minus 8 and 10 to the minus 16 and so on. That is observed already from this computation. Look at here. Now, correction terms are really more or less doubled digits, so that this theory is already verified. And here C is some positive constant. Such a convergence is called a quadratic convergence. Newton method is very fast, and usually we say that it is a quadratic convergence, and because of that inequality. Okay, here let's try to see one more example for fx, and fx equal arctangent x. So we want to solve the problem. Now, once you try to solve the equation, then only the solution is x0. Here, arctangent, the minimum value is, the asymptote is minus pi over 2, and that side, the asymptote is pi over 2. So that arctangent has value here minus pi over 2 to pi over 2. Okay, so that's asymptote and that's asymptote. Okay, now it's increasing function, and here only the root is 0. Okay, we'll use Newton's method to find the root, and starting with x0 pi over 2 and x0 pi over 4. Here, this is implementation. F is defined now. ATAN, the arctangent in MathTalent, is expressed in this way. Now, its derivative is the same as 1 over 1 plus x squared. So here, derivative is defined along with the df. Okay, start with now pi over 4. Then now let's see 5 iterations. F of x divided by df of x. That is correction term. Now correction term is subtracted to get new update, and we try to print out along with pi over 4 and pi over 2. Okay, here we have result for 5 iteration. Once you start with x equal pi over 2, then as you can see over there, now x is diverging. The values go to left side, right side, left side, right side, far left side. Now next iteration will go far right side, so it is diverging. And correction terms are given in this way. And also, as you can see over there, now the magnitude and one side, negative, positive, negative, positive, and then it's approaching to either minus pi over 2 and positive pi over 2. But if we are choosing x0 pi over 4, then look at here. Now the 0 is the root. Now x1, x2, and x5, as you can see over there, now it's about 10 to the minus 2. That is 10 to the minus 6. And now that is 10 to the minus 18 is better than square. In fact, this is a symmetric shape so that it has cubic convergence rather than quadratic. In fact, one order higher, such a higher than expected, mathematically expected order is called superconvergence. Because of symmetry, it has some superconvergence. And also the same here, f of xn is now 10 to the minus 2, 10 to the minus 6, and 10 to the minus 17 is almost the cubic convergence. Okay. So once the initial value is near to, so that is near to 0, and this is somewhat far, so that it is divergent. Pictorially, we can explain in this way. It's pi over 2, then that is larger than, yes, 1.5. So that you start with here now, and around here, then x0 is around here now, then tangent line will hit here around there, okay, so that x1 will be, okay, it is hitting, in fact, around here. I exaggerated too much, so that right now it is hitting around here, so that from this one, so the value is now minus 1.9, so that from here you can make, again, tangent line, that is around 30.14, which means that around there, it is the tangent line, and is now, oh, okay, just a moment. It's x-axis. In fact, okay, tangent line is hitting here, around here. So that from the point, go here now, so that hitting here. Okay, so that's x-axis. So that from here, now tangent line is hitting around there. So that point is now that one, and so on. Okay, so it is eventually go far this way, go far that way, and then blowing up. Okay, that's the end of the section. Thank you.